Welcome. In this session, we'll explore the gradient inequality for a function that has a vector argument. Let's consider a well-behaved function. So let's consider, and by well-behaved, I mean an analytic function, and an analytic function is one where its Taylor series always converges. So let's suppose we have a well-behaved function that has a vector argument and produces a real level. And let's restrict the domain to a convex set, and we'll write that as V, and it is a not strict subset of all of the possible vectors. And let's require F to be convex over this convex set. And that means that if I take any two arguments that are in the convex set and I evaluate them, that F is a convex function between those 2 points. Now let's recall, that's a consider, and now let's recall the Lagrange form of the Taylor series. And that is that for any particular vector that is in this convex set, there is a vector, and this is usually written as a vector C, that is also in that convex set, such that, and so this is the vector form of the Taylor series, the function at any argument that is in the convex set V can be expressed as, we can evaluate the function at that particular point, and then we can add the gradient one form of the function evaluated at that particular point times the difference between our argument and that particular point, plus, and then the Lagrange remainder form is that this is the difference between our argument and our particular point transposed times the Hessian evaluated at that particular point times the vector difference. And, oh, sorry, that's not exactly right. That is supposed to be the vector C. So that is the Lagrange form. So what can we say? Well, what this implies is that because F is convex over that convex set V, we know that the Hessian matrix of the function at that Lagrange vector has to be symmetric, positive, semi-definite. We can't, if it was strictly convex, things would be much more complicated. If it's convex, it's possible that it's semi-definite, okay? And that implies that, so if we recall a symmetric positive semi-definite matrix, that means if we pump any vector transpose in times the vector times the matrix times a vector, that's greater than or equal to 0. So in particular, if I pump W minus W0 transpose times the Hessian matrix evaluated at that Lagrange vector times that difference, that is at least as big as 0. And so the gradient inequality is this. So the gradient inequality, this depends on a bunch of assumptions, right? What we're assuming is we have a convex set and that f is a nice function, it's analytic, and it's convex over that entire set. Then, after using the Lagrange form, what we get is that the function at any point in V is at least the function evaluated at some point plus the gradient 1 form at that point times the difference. And let's briefly recall 1D before we go into a 2D example. In 1D, what we said was that if a function is locally convex and we take any point along the, here I'm drawing it as though it's a vector. In our scalar version, this was just some value t0, that what it says is that the tangent line for a scalar argument is a lower bound on the function at that point, and that if we evaluate any w in this convex region, that it's always above that tangent line. Now, let's take a look at what that means for a function that has a vector argument. Let's explore this in a 2D example. Suppose that we have a quadratic form with the matrix being the identity. So this would be a surface of revolution of a paraboloid. And what we see is that this paraboloid is lower bounded. Instead of being a tangent line as we had in scalar land, it's a tangent plane. And as we get into higher dimensions, a quadratic form would be, its lower bound would be a hyperplane. So this is a visual example of what we mean by the gradient inequality in optimization. Let's summarize this lecture. A convex function of a vector argument was a direct extension of the idea of convexity for a scalar function. A convex function is invariant to scaling by a non-zero multiple, by a non-negative multiple, and by addition of two convex functions. The gradient inequality states that any convex function lies at or above its tangent plane in the local region, and a level set fills in a level curve. We observe that a convex set has to contain a line segment that connects any 2 points that are within the set, and the level set of a convex function is a level set. This is something that we didn't prove, but it's a really important property that we'll rely on later.